right here you're seeing exemplified a multiplication, because if you work your way from the left-hand side to there, you're really just multiplying that term with that particular polynomial, which can be accomplished, of course, just by using the distributive property there. A number of ways in which we're asked to multiply expressions would be to, of course, be asked to multiply, and of course the product of something is the result you get from multiplying. Sometimes you might also see the term expand, so when you're expanding an expression, like expand usually means to make it longer or larger, right? So expand does mean to multiply. Also write it in standard form, because that would be in standard form because you've got separate terms, whereas right here that's not considered in standard form, and we'll talk about that a little bit later on, as well as simplifying. So it does turn out that this expression right here is in simplest possible form when you've got it in standard form or you've got separate terms going on. It turns out that this right here is not in simplest form. It's actually in a factored form, because this thing is in parentheses. That really is like kind of one little like quantity, that yellow quantity right there, and then this quantity right here, which I put in a different color, is really multiplying with the yellow. And so you really have the product of like a teal thing with a yellow thing, which means it's in a factored form. And actually anything that's in a factored form is not considered simplified in math. So it does turn out that if you are asked to factor, it's really just like the opposite of multiplying. It's just working backwards. So it does turn out that if you have this expression right here that's in simplest form, you can factor it if you write it as a product of its factors. What that ultimately is really going to look like for this example is you could take out like a -8, because -8 and 16 and -40 are all divisible by -8. And what that then leaves is it leaves just a +1 here and a -2 here and a +5 here. But then also you could take out like x to the third as well, which then really leaves you with just like 1x to the second here minus 2x plus 5, and that would give you a factored form of that particular expression. So whenever you're asked to factor, right, based on how I defined it earlier, you're writing an expression as a product. And so we're going to go through some examples that are just algebraic, in which we're trying to factor an expression. So a one-word instruction, factor, right? So to factor means to write something as a product of its factors. Now, when you do factor, the first step in any factoring is always to factor out the greatest common factor. So not just a common factor, factor out a greatest common factor of all the terms, if there is one that's not just a 1. So with this very first expression here, we have 110x to the third plus 25x squared plus 45x. So what you're going to want to examine first of all is what common factor there is that's the greatest that you can factor out. So of 110 and 25 and 45, it does turn out that 5 is something that they're all divisible by, and it's actually the largest. So you're able to take out a 5, and then also comparing x to the third and x squared and x, you can also take out an x. So we're not asked to identify the greatest common factor here. That's part of the process. We actually want to factor this. So we found the greatest common factor. I wrote the greatest common factor of 5x, but really you can use that 5x and just kind of think like reverse of the distributive property and think, okay, so 5x, if I were to distribute it, it would multiply to something right here that then would have to equal 110x to the third, right? So you have to figure out like 5 times what equals 110, or what is 110 divided by 5, right? So it ends up being positive 22, but then you would also need x to the second right there, because x times x to the second would equal x to the third. Then you would also have to have the addition of another term, and you have to think, okay, 5x times what is going to give me this 25x squared. So it does turn out that 5 times 5 is 25, and you'd also need an x there to get your x squared. And then finally, you have to think, okay, 5x times what is going to give me 45? Well, 5 times 9, but then you wouldn't need an x with a 9 since that x from the 5x would distribute there. So it turns out that this right here would be a factored form of that expression, and the reason why it's factored, so you can kind of see this in color, is that we've written it as a product of that factor with this other factor. So that orange and pink are kind of factors of the algebraic expression that you're seeing right there. Jumping over to 3n plus 3, you can see that both 3n and 3 are going to be both divisible by 3, so you're going to factor out a 3 from both of these terms, but they both don't share variables, so you can't take out a variable factor. So you'll just factor out a 3 as a common factor, so think about 3 times what is going to give me 3n, and it just turns out that this is going to have to be an n, and then you have to think, okay, 3 times what is going to give me a positive 3, so that's going to have to be a 1, and that right there would give you a factored form of that particular expression there. The third one here has c to the third plus c. So in terms of numbers, they're only really divisible by a 1, but you can at least take out a single c. So if you do factor out a c, it turns out that if you then multiply c with c squared, that gives you c to the third. And then also if you multiply c with 1, that's going to give you a c. So that's going to give you that factored form of that expression by factoring out a greatest common factor. And then for this fourth example in this section right here, when you compare 6 and 24 and 72, they are all divisible by 6 at the greatest. You definitely want to factor out a 6. And then you have to compare a to the 6th and a to the 4th and a squared. A squared would be the greatest among the common factors. So you're also going to factor out an a squared from everything. So you have to think that if I I'm distributed 6a squared to this term, and I want it to equal 6a to the 6th, then I'm going to need that first term in the parentheses there to be a to the 4th. To multiply to equal negative 24, we're going to have to multiply 6 by a negative 4, so you're going to have subtraction of 4, and then also a squared there, because you need a squared times a squared to equal a to the 4th. And then finally, 6 times negative 12 is going to give you 72, but then that a squared is going to distribute to give you the a squared, so you don't need an a to go with that negative 12. So then that would give you that final result right there as a factored form of that polynomial by factoring out a greatest common factor. Some things to think about when you've got polynomials where the leading coefficient is negative. Now, when I say the leading coefficient, like the leader, and the way you determine the leader in a polynomial is the term that's got the highest degree or the highest exponent involved. So you can see that, yep, 4 is the highest exponent there and 3 is the highest exponent. Now, in each of these examples, the leading coefficient is negative. So whenever you are factoring out a GCF of an expression, you should always factor out a negative. So that should always kind of be in front. So with this example right here, you're going to want to factor out a negative, and then 9, 15, and 18. They're all divisible by 3 at the greatest. So you have to factor out a negative 3 from all of the terms, and then x to the 4th, x to the 3rd, and x squared all are divisible by x squared. So you factor that out as your GCF. So of course that's going to kind of like reverse your signs of everything because you're factoring out a negative. So here you're going to get like a positive, right? Because negative 3 times 3 will be negative 9, and x squared times x squared is x to the 4th. And then here you're now going to have a subtraction because you'll have a negative times a negative to create that positive. It'll have to be a 5x to get you 15x to the 3rd there. And then finally you're going to have a positive to multiply with that negative 3, a positive 6 right there with no x. So that would give you that factored expression there. And then the one right next door also has a negative leading coefficient, so you definitely need to factor out a negative. Number-wise, you have a 4, an 8, and a 1, so they're not divisible by anything other than just a 1. But in terms of variables, you're going to have to factor out an m. So negative m is going to be the GCF that you'll want to factor out. And then from there, you're going to be left with a 4m squared plus an 8m plus a 1 when you think about how that negative m would distribute to everything to create that negative 4m to the 3rd minus 8m squared minus m expression. And then here, again, a one-word instruction to just factor the expression. So in this first example right here, you're going to see that you've got a little bit more stuff going on because you've got lots of a couple variables involved in that term as well as in that term. So you got to start by just comparing the numbers. So 18 and 45 are both divisible by like 3, also by 9, and I think 9 would be the greatest. You have to factor out the greatest, so factor out the 9, but then also compare the f variables, 1s to the 10th and 1s to the 7th, so the greatest they would share is f to the 7th, and then g to the 7th and g to the 8th, the greatest they share is g to the 7th. So that right there specifies the GCF that we can factor out, and then from there you have to think about multiplying to equal 18, so 9 times 2, right? And then also multiplying to equal f to the 10th, so if you start with f to the 7th, then you're going to need 3 more f's to multiply by, and then you have a g to the 7th, but you already have a g to the 7th, so you don't need any g with that term in the parenthesis then, and then we can put a plus sign, and then 9 times 5 will give you the 45. To get f to the 7th, you already have that, so you don't need an f. You need g to the 8th, you already have g to the 7th, you're just going to need one more g right there, so that gives you a factored form of that expression. And then right next door, you've got 8 and 16. Now, 8 and 16 are divisible by like 2 and 4 and 8. You need the greatest, which is going to have to be 8. They don't share any variables, though, so that's going to be the only thing you'll have to factor out. So it does turn out that 8 can distribute to n squared to give you the 8n squared, and then 8 can also distribute to a negative 2 to give you negative 16, and that gives you that factored form that you see there. And then at the very bottom right here, again, another one-word expression to factor these, right? So when you compare the terms and you look at the numbers, 25, 30, and 4, they're only divisible by 1 only, right? That's the only common factor that they have. So we don't have to worry about that. And then variable-wise, the last one doesn't have a variable. So really the greatest common factor of this is just a 1. So if that's just a 1, what that tells you is that you really can't take out a common factor here, which means that really this expression seems to be not factorable, right? So what we can say is that this expression right here is not factorable, and so what that kind of tells you about the expression is that it's kind of prime, right? So there was an example earlier where I had like the number 19, right? And we said that 19, you can't really factor it because it doesn't have any factors other than really like 1 in itself, right? And so therefore, similarly, we can kind of say the same thing with algebraic expressions as well, that if you can't really factor it, then we would kind of denote it as a prime expression. It's not able to be factored. The example right next door, the same sort of case is happening right here because 2 and 5 don't have any common factors and they've got different variables involved. So this guy right here, you're not able to factor it. So same conclusion, you could say that it's not factorable, or you could also just say that the expression itself is prime.